Welcome to Linear Algebra. Today we are going to explore one of the most important concepts in all of mathematics, the vector space. Imagine you are playing a video game where you can only move your character by walking forward, backward, left or right. No matter how you combine these movements, you always stay on the flat game map. You cannot suddenly fly into the sky or dig underground. A vector space is exactly like this game map. It is a specific mathematical universe with strict rules, and understanding these rules will unlock powerful tools for physics, computer science, and beyond. Now that we have our video game analogy, let us define this formally. Why does this concept matter? Because we need a reliable environment where mathematical operations do not produce impossible results. A vector space is simply a collection of objects which we call vectors. Along with these vectors, we define two specific actions: vector addition, which combines two vectors, and scalar multiplication, which stretches or shrinks a vector using a plain number, known as a scalar. For this collection to officially be called a vector space, these actions must perfectly obey 10 specific rules or axioms. If even one rule fails, the entire collection breaks down. Let us look at the first and most critical rule: closure under addition. Conceptually, this means that if you mix two colors from a specific paint box, the resulting color must also belong to that same paint box. In our formula, U and V represent two vectors, and the symbol in the middle means belongs to. Capital V represents our entire collection, or vector space. If you add vector U and vector V together, the new resulting vector must still live safely inside V. If adding them somehow creates an alien object that pops out of our allowed universe, the collection is not a vector space. This formula we just saw leads us to another fundamental rule about addition: commutativity. Think of walking 3 blocks north and then 2 blocks east. You will end up in the exact same spot as if you walked 2 blocks east first and then 3 blocks north. The formula simply states that vector u plus vector v is exactly equal to vector v plus vector u. The order of operations does not change the final destination. If a space somehow gives you a different result depending on which vector you start with, it violates this rule and cannot be a vector space. Moving forward, every valid mathematical universe must have an origin point, or a concept of doing nothing. This is represented by the zero vector. The formula shows that if you take any vector u and add the zero vector to it, the result is simply u. It leaves the original vector completely unchanged. In daily life, this is like saying if you have $5 and I give you $0, you still have exactly $5. If a collection of objects does not contain a zero vector, it is fundamentally broken and cannot be a vector space. Now that we have a zero vector, we must be able to return to it. This brings us to the additive inverse. Conceptually, if you walk 5 steps forward, you must be able to walk 5 steps backward to return to your exact starting point. In our formula, negative u represents a vector that has the exact same length as u, but points in the exact opposite direction. When you add a vector to its inverse, they perfectly cancel each other out, bringing us back to the zero vector. If a space does not allow you to reverse your steps, it fails the test. We have covered addition, so let us look at our second main action, scalar multiplication. Just like addition, scaling a vector must be a closed operation. The letter C represents a scalar, which is just a plain real number like 3 or negative 1.5. If we take our vector u and multiply it by c, we might stretch it, shrink it, or flip its direction. However, this new resulting vector must still live inside our collection V. If stretching a vector makes it leave the allowed universe, the collection is not a vector space. Before we move on, let us see this with a concrete visual. Look at the flat shaded plane on your screen. This plane represents our entire allowed universe, the set V. Notice what happens when we add the arrows u and v together. The resulting dashed arrow, u plus v, stays perfectly flat on the plane. It does not point upward off the page. Similarly, when we stretch the arrow u by a scalar c to make it longer, it remains trapped on that same flat surface. This diagram perfectly captures what we mean by closure. The operations keep us safely inside the boundaries. Now that we understand what closure is, let us look at how it works in practice by proving that the standard two-dimensional plane is a valid vector space. We are given the set of all 2D vectors called R squared, and we need to check if it passes the closure under addition test. We start by defining two arbitrary vectors, u and v. The symbols x1 and y1 are just plain numbers representing the horizontal and vertical components of the first vector. Because these are generic real numbers, these vectors can represent any point whatsoever on a flat map. Continuing with our proof, we now add our two generic vectors together. To add vectors in a matrix format, we simply add the numbers in the matching positions. The top row becomes the sum x1 plus x2, and the bottom row becomes y1 plus y2. Because adding two plain real numbers always gives you another plain real number, our final result is still a column containing exactly two real numbers. This perfectly matches the definition of a 2D vector. Therefore, the result still belongs to our original set, proving physically and mathematically that the 2D plane is closed under addition. So, we have proven that the standard plane holds up. This brings us to an important question. What does it look like when a set fails? Not every collection of numbers is a vector space. Consider a restricted set of 2D vectors where both numbers must be positive or zero. Visually, this represents only the top right quarter of a standard graph, known as the first quadrant. To prove a set is not a vector space, we do not need to check all 10 rules. We only need to find one single rule that breaks. Let us test this restricted set. Let us set up our test. We are given a set restricted to positive numbers, and we are asked to see if it survives the strict rules of a vector space. We will test the rule of closure under scalar multiplication, which is often the easiest way to break a restricted set. We choose a specific vector u with a horizontal component of 3 and a vertical component of 4. Because both are positive, this vector legally belongs to our set. Next, we choose a scalar c equal to -2. Remember, the rules state we must be able to multiply by any real number. Now we perform the scalar multiplication. We multiply both the top number and the bottom number of our vector by the negative scalar, -2. The resulting vector has a horizontal component of -6 and a vertical component of -8. This new vector points down and to the left. It has completely escaped the allowed top right region and landed in the bottom left quarter of the graph. Because multiplying by a negative number forced the vector outside the allowed collection, the set is not closed. This single violation invalidates its vector space status entirely. Now that we have seen how strict these rules are, you might wonder why we spend so much time defining them. Why does this matter? Because once we prove a collection is a vector space, we instantly unlock hundreds of powerful mathematical tools. In computer graphics, the screen you are looking at is treated as a massive vector space, allowing the computer to smoothly rotate and scale 3D objects without them distorting. In physics, forces exist in a vector space, guaranteeing we can calculate stress on a bridge predictably. Even artificial intelligence processes human language by treating words as vectors in a space with thousands of dimensions. We have covered a lot of ground today. So let us review the most important ideas. First, a vector space is simply a well-behaved mathematical universe. It is a collection of objects that can be added together and scaled by numbers, while strictly obeying 10 logical rules. The most critical of these rules are closure under addition and closure under scalar multiplication. These ensure that combining or stretching objects never forces them outside the collection. By guaranteeing this predictable behavior, vector spaces form the absolute foundation of linear algebra. You now have the conceptual tools to explore this universe further. Great work today.